primary use of the IOBs is for registering data. In this slide, you see that there are 6 registers associated with the IOB to support the use of double data rate applications. As you can see, there are 2 registers for input, 2 for output, and 2 for 3-state enable. However, the IOB can still be used for single data rate applications just as easily. Each register supports separate clocks and clock enables for input and output, but the set and reset signals must be shared. To clock the DDR registers, remember that you can use any pair of the PLL outputs that are 180 degrees out of phase, such as clock 90 and clock 270 outputs, likewise the clock 2X and clock 2X phase shift by 180, or even the clock FX and the clock FX phase shift by 180. Besides the register and select IO resources, there are also SerDes functionality built into each IOB. This includes both parallel to serial and serial to parallel conversion. This is a programmable functionality that can decode a wide range of signals. The O-SerDes I-SerDes combination is probably one of the most useful and radical developments. Many issues that you would traditionally address by using the FPGA fabric are handled within these blocks now. Tasks such as trading pattern recognition, clock to data alignment, and crossing of clock domains between high-speed serial I/O and slower parallel clock domains can now be accomplished with the dedicated logic included in the SerDes resources. When we couple these resources with the I/O clock resources, this feature becomes very significant and well suited for source synchronous applications. Now, we'll discuss the clocking resources and that corresponding REL. So we'll discuss that in another REL, and you can check that out. The I/O SerDes capability includes input and output SerDes resources. There is an O-SerDes parallel to serial converter for both OQ and TQ. It is arranged as a master and a slave IOB pair to allow for differential inputs or larger single-ended bit widths. So not only can you complete, say, a 6-to-1 parallel and serial conversion, but when you pair these 2 pins appropriately, you can do larger parallel and serial conversion. For this to be done, an appropriate master serial pair must be found on the die. You can't just pair any 2 IOBs and make them a master-slave pair. So you'll need to either check the datasheet or use pin ahead to find out which of your pins are already pre-grouped. Each flip-flop has 3 control ports: clock, clock enable, and a set reset port. You have to remember that the clock enable and the set reset ports are active high. This is important when coding your HDL for the flip-flops. Likewise, note that there is not a separate set and reset port, just one port that is either set or reset. And this port can be asynchronous or synchronous. This is important because your synthesis tool should be able to map the set or reset to a LUT input if it is synchronous. This gives you more flexibility that is necessary for the tools to pack the most logic into the FPGA and get high speed, since all 8 flip-flops are required to share the same control signals. So our recommendations are to design for active high control signals and build with a synchronous set or reset. Besides building synchronously, you should also try to use the FPGA's global reset functionality whenever possible. This will allow you to perform a global reset on your system using a dedicated routing resource. This will require the instantiation of the startup component from the Xilinx Unified Library that pertains to your chosen device family. Now, this will save you from routing a high fan-out signal to all of your FPGA resources, which is a significant amount of routing. And don't forget to keep your control signals active high, so you don't need a local inverter to be mapped to each control signal input. These are not dedicated in the silicon, and that would force the synthesis tool to waste a LUT input. The reason we have spent some time discussing the limitations of control signals is that they can limit your ability to get high device utilization and high speed out of your FPGA. The reason this is necessary is the implementation tools can only pack related logic together in the same slice, since there are a limited number of inputs to each slice. This is important with registers since all of the flip-flops share the same control signals. Likewise, if the tools are going to use the 5-input LUT configuration, it has to be able to find another combinatorial function with 5 of the same inputs to be grouped into the same slice. You see, it's all about grouping related logic into the same slice. If the tools can pack related logic together, it does not end up wasting LUTs and registers. As I mentioned earlier, your synthesis tool can map clock enable and synchronous set or reset functionality to a LUT input. This is very powerful for being able to group registers into the same slice, since all the flip-flops are required to share the same control signal. In this example, we see how a clock enable and a synchronous set or reset is mapped to a LUT input. Now this is very helpful, but a job only your synthesis tool can do. But if you build with an asynchronous set or reset, then it can't happen. In that case, the asynchronous set or reset would be forced to a register control port. Likewise, if you build with an active low control signal, the LUT will be required to invert the control signal.